Hello and welcome to my talk. My name is Duncan McGregor and today I'm going to share with you a little Lisp flavored Erlang, some extempore, music synthesis and recording, and how they all come together in the Undertone project. These are the topics I hope to cover. And this is a lot, but we should be able to get through most of it. Here's a little bit about me, but we can skip past that. Here are some snippets from my brushes with music, most of which is in the relatively distant past. In point of fact, the last musical performance I gave was as a pianist in a chamber music quartet when I was 17. It's been a while. Between then and 2014, when I was 42, I met Andrew Sorensen, pictured here, after his extemporary live code performance at OSCON. And yes, that dude with the short hair is me. Andrew and I talked about live coding, my interest in using LFE-OTP along with extempore, and if I remember correctly, he mentioned conversations that he and Joe Armstrong had about extempore and Erlang, and some potential collaboration between the two of them. He then shared his performance code with me. I created a variation on it, blogged about it, and thus began a slow reignition of my passion for music. As a side note, a few years ago, I picked up the guitar again, and more recently, I've been relearning piano and keyboards. I'm studying music theory and even taking some online music courses. It has been fantastic and a much-needed outlet. Later, after the OSCON conference, chatting with members of the LFE community, we talked briefly about exploring sound synthesis libraries in LFE, but none of us had the time or interest to take things much further. Then, years later, along comes this gem of a blog post from Erlang Solutions by Alexander Lisecki. Upon seeing this, I immediately did this. And this, in essence, porting the code in that blog post to LFE. The path from there to Undertone was mostly straightforward. That blog post was about generating single tones, and I wanted to be able to do more than that. I wanted to control synthesizers and run services. In short, make music. I read everything I could on Erlang and MIDI and music, retracing a lot of Joe Armstrong's steps that he made from the mid-2000s up until a few short years ago. I implemented basic support for Super Collider, upon which much of his work depended, but was frustrated by the lack of musicality in that particular system, at which point I returned to extempore and began integrating it into Undertone as well. I added enough functionality that I could generate a demo song with 9 separate tracks of synthesizer being played. All of those were created using Undertone itself. The end result was featured in the Lambda Days teaser video for this talk. There's a lot to unpack in that video and what was recorded there, and a brief overview of the architecture would go a long way toward giving you a good idea of what Undertone really is. But before that, how about some music? The demo I had originally planned showing you would have been a presentation of the code that was used to create the music in that teaser video. Honestly, though, that's pretty boring. Some of the manually defined chord definitions, some elementary transformations of Lisp using maps and fold, etc. Not so much pizzazz there. I then decided to add support for MIDI control code so I could show you how LFE can control analog synthesizers like the classic Minimoog, radically changing the sounds even without adjusting the notes. After updating Undertone for this and creating a demo, I presented it to the DFW Beamers and decided to also include it in today's talk as a bonus. Here it is. We're going to start off the demo by pasting LFE code, all the setup, start up the sequencer, set up some basic effects, chorus and delay. numbers and names over on the far right are MIDI control codes. They've been mapped to the red knobs here on the synthesizer. They allow us to control those particular knobs by sending a message for that particular control code. When you see a CC here, that's a control code function being called that sets a particular value on the synthesizer. When you see a CC ramp, that is taking a particular value, going over another duration, finally ending with a new value. That is implemented with Erlang's timer apply after. And there you have it. But I still wasn't quite satisfied. I had promised to show conference attendees something with generative music, and these demos kept missing the mark. So I created a new piece with new code, and that's what I'm going to show you next. It's not a lot, it's not amazing, but at least it shows some aspects of generative code, and it's a first step in that direction. The first thing I'm going to do in the demo is paste all the code into the custom Extempore REPL. And we can look at our session, see all the commands that we've pasted in order indexed for easy reference. Now I'm going to start up the sequence, progression. And initially it's just the sound effects channels playing. And I'm going to slowly bring up the background pads. The accompanying tracks is coming up in volume now. Sort of a bass organ sound. And what you're hearing is the chord transitions being played, as you can see in the terminal window. And this is the Markov chain in action. So for every chord that's currently being played, when it's time to switch, it looks at the available legal ones that it can transition to, and then it selects one. How long, how loud, these are all determined in our function, our progression function. Easily changeable, both in real time and ahead of time. And now we're going to bring up the sequencer tracks. The sequencer is defined here. This is also possible to do in pure LFE. We're doing everything in Extempore right now. And that's where the progression actually starts the sequencer. And the sequencer is selecting its chords and notes dependent upon the current progressions being played. And we can see in the plugin the notes actually being played. Again, all of this coming from the LFE REPL, or rather LFE running the Extempore REPL. sound here on the Berlin School. And now we've just transitioned back from major into the minor key. All the progressions played so far. This could actually be done in with LFE code, the tweaking that we're doing right now with the knobs. There's another demo that shows exactly how to do that. Just changing the frequency of the filter. You'll hear a few glitches here and there. I had some problems with overloaded plugins and buffers, so if you can forgive that, I'd appreciate it. Bring the frequency back down. Make sure that we don't try to transition back out of the minor. We stay minor from here on out. So just set that threshold really high. And there you have it. So here's a view of the system you just saw demoed, represented with the C4 style of architectural diagrams. Don't worry though, we're just going to look at 2 of the 4. Lest you get the wrong idea, only a small portion of this diagram is Undertone, and I should point out that the hard work of sending MIDI messages or playing its own sounds, as the case may be, is all done by Extempore, Andrew Sorensen's open source live coding software. Extempore runs a TCP server to which we can connect, and then from there gain access to the operating system's audio layer, MIDI devices, and the like. Undertone spawns Extempore as a managed OS process, starts a TCP client, and optionally starts open sound control clients and servers. All of this gets stuffed into a supervision tree that will restart these components should you push them beyond their limits, all without crashing the Erlang VM. Now, if we zoom in on Undertone's purple box or container, we can see a little more of what's going on under the bonnet. The container view of Undertone shows which components are connected to each other and how. The gray box in the upper left is where the first demo took place. All the commands entered there were sent via the Undertone managed TCP client to the Extempore compiler server. The gray box in the middle right is what you saw when looking at the terminal in the second demo, where, after pasting all the Extempore code, we viewed the indexed history of the entered scheme forms, and where all the logging output was. That REPL, while written in LFE, has its own commands separate from the LFE REPL. Extempore proper doesn't actually have a REPL of its own. The standard way of interacting with it is by means of a text editor, such as Emacs, that's capable of sending scheme forms to the Extempore TCP server for on-the-fly compilation. In short, everything within the dashed purple border here has been written in LFE. Also, note that the blue Extempore box actually represents LFE spawning the Extempore process at the OS level and managing that spawn port and associated state in a gen server. And here's a quick textual overview of what we just covered. So, what can Undertone do? In Undertone, you can run functions that control a digital audio workstation, like the one pictured here, moving faders, enabling tracks, recording, looping, the list goes on and on. You can not only control software devices like the Moog modular synth I showed you in the demo, but you can also control physical devices like these two, which, by the way, were generating music written in LFE when the pictures were actually taken. On the left is a chord Chronos, and the right shows a desktop analog synth, a Minimoog clone by Behringer. Practically speaking, though, this is how I'll be using Undertone. I'm really looking forward to finally getting there. The software's made a lot of progress in the last few months, and it should be quite a lot of fun. Okay, so here's a quick refresher on what we've covered so far and what's left to go. It's probably a good bet that most attendees at the conference are more familiar with Erlang than LFE. So here's a little comparison to help you get your bearings. This is the same function written in each, demonstrating some basic recursion as well as pattern matching in the function heads. If that wasn't complicated enough, there are two more languages involved here as well. This is Extempore's XT-lang, which provides low-level access to all aspects of the Extempore system. And this is Extempore's higher-level language, a derivative of TinyScheme. This is what most Extempore performers use, and in fact is what you saw me pasting into the REPL at the beginning of the second demo. In both cases, for both of those dialects of Extempore, developers are accessing mutable data, changing elements of the system as it runs, and using those changes to generate music. While perfectly suited for what it does, the appeal to a functional programmer is perhaps not immediately apparent. But a second or third glance might inspire such a programmer to look at a classic sequencer, such as this one, which, by the way, were based upon telephone switching hardware. And upon those glances, use immutable data structures and all languages' vast resources to carefully manage that global state with code like this. In the first demo, you saw me calling functions such as these to start, stop, modify, and change the notes in the sequencer in LFE with LFE code. This approach to managing extempore state, as you may well imagine, helps a programmer to keep much better track of what's going on and how to change the system in a predictable manner. Next, we'll touch on the topic of sound synthesis, and in particular, its fundamental concepts and how well these map to the principles of functional programming. This topic deserves a little context, though. So let's take the scenic route. This is a picture of the telharmonium, or the dynamophone, an early electrical mechanical musical device created in 1896. Only the smallest portion is shown, essentially the console. The bulk of the instrument remained housed in the basement of the performance hall, connected to the console via electrical wires. And I do mean bulk. The second and third iterations of this instrument weighed in at 210 tons. On the other end of the spectrum was this device, the theremin, created in the 1920s. It was this device that originally captured the imagination and electrical engineering skills of Bob Moog as a teenager, the eventual inventor of the Moog synthesizer. His company still manufactures theremins today, and when you hear the sound, it's the classic haunting woo-woo sound you hear in the 50s sci-fi films. And if you're a fan of murder mysteries, a Midsummer Murders theremin is played in the theme song for that show. And then there was Peter Zinoviev, who had this kit in his garden shed in Britain. He was the son of a Russian princess and the first private owner of PDP-8's personal computers. He actually had two of them. Both he used for sound synthesis. Zinoviev worked with all sorts of amazing musicians, and I think one of the Beatles even visited him, but he wasn't interested in pop music. He was very, very passionate about electronic generated music. He and Bob Moog had a lot of the same ideas, created independently of each other, both using voltage control filters to produce sounds. A nice bit of convergent evolution. By the mid-60s, sound synthesis had converged upon the basics of what is now called subtractive synthesis. An oscillating sound source acts as input for various filters, amplifiers, modulators, etc. Here's a graphic depiction of what has become one of the foundations of sound synthesis, originally used to electronically model the behavior of physical musical instruments. This is a depiction of an envelope, or how a sound changes over time. It was originally implemented with a doorbell switch, initiating the envelope trigger event, and a capacitor to gradually release the voltage associated with a musical note. In essence, then, what we have here is a function generating output, the key press, and then that output being transformed in a specific repeatable manner given the state of the envelope at any given point in time. To provide some context, the ADSR parameters of the envelope generator are shown here in the third and second to last modules on the right, each affecting different parts of the signal chain. This is a diagram from an introduction to modular synthesis on the website synthesizer.com. It represents a very simple setup, or patch, where MIDI signals are providing the messages that generate the initial voltage. Subsequent modules in the signal chain modify that signal, or are used to affect another module that will ultimately modify the total output of the system. One interesting difference between analog computing, such as this, and the functional programming we are more used to, is the temporal element. We generally don't run into something analogous to this at the language level. Rather, we see this in I/O systems that change over time, such as messaging or stream processing frameworks. Of course, from the mathematical perspective, this puts us solidly in the realm of the calculus and partial differential equations. For the electronically minded, here's a logical diagram of the previous patch cable diagram. This should help make the point more clearly that sound synthesis of this form is reducible to the standard mathematical approximations of electronic circuit operations, arguably deeply functional in nature, if thoroughly within the domain of I/O. Extending the patch example I've just shown to something in practice, here's a screenshot of the same Moog modular synth I used in the demo. Note that this is a very simple patch. However, despite the increasing complexity, the same principles apply, with the various modules producing outputs that become inputs of other modules. As you might be intuiting with the cable crossing scene here, the degree to which one may apply the outputs of one module may lead to an exponential increase in complexity, and could result in taking the thing to its logical extreme, which gives us the likes of Keith Emerson from Emerson, Lake and Palmer. His synth patches are famous for their great sounds and stunning electronic complexity, and he had a monster of a custom Moog setup, which was equally famous. Oh, what a lucky man he was. So what's next for Undertone? I've created tickets for efforts such as deeper support of extempore and native LFE, live capture of music recorded as LFE data structures. And that's actually in progress now, and I've had success pulling in LFE data from physical MIDI devices. I also want to continue working on the LFE and Extempore REPLs, and I want to create a hybrid REPL that supports both languages simultaneously. Digital signal processing from LFE itself, without having to go into without having to have an LFE programmer write extempore code or scheme. That'd be nice to have. It does require a lot of work at the language level, a lot of parsing. I also want to add more support for open source synthesizers. There's a lot of really fantastic stuff out there, some great open source synthesizers, and it would be nice to have their MIDI control codes and usable by LFE programmers who wanted to use those synthesizers. And I want to get a lot of practical use in generating music, exploring music theory, and just listening. So it'll be fun to create stuff that you can just let play. I'd like to thank Konrad Barsky for his allowance of using the images. I was going to add a lot more of his images and create a longer story around Lisp and distributed Lisp, but it just didn't work out. So the few that I used, though, I do appreciate.